Our next big topic is recursion. And initially I had made a Zybooks assignment to read the first three sections, 16.1, 2, and 3, on recursion. But I looked at it this morning and I thought that the sections 2 and 3 were a little difficult for students who were meeting this for the first time. So I also thought that I would look at 16.1 with you. So it starts out by talking about algorithm, and this is the standard way of speaking about it. They're like recipes. You do something, you do something, you do something. Unlike recipes, with an algorithm, you have to do it in order. With this recipe, it's possible that you could add the water before the lemon juice and everything would turn out okay. But we know what an algorithm is. Let's look at what a recursive algorithm is. So the recursive algorithm breaks down our big problem into smaller sub-problems. It could be just one smaller one, or it could be more than one. And then it does the exact same thing on each of those smaller parts. So in this example, how to mow a lawn, well, you break that down into two parts. You mow the front yard, which is really mowing the lawn. It's just a sub part of the lawn. It's the front yard. And then you do the exact same thing on the backyard. Well, if we look at mow the front yard, we can break this down into two problems, mow the left and mow the right. Similarly for the backyard. And then each of these mow the left fronts can also be broken down into smaller portions. And so that is the idea behind recursion. Let's look at some examples here. They're asking which are recursive. So I need to help n people. Well, if n is 1, just help that one person. Otherwise, help the first half of the people and then help the second half of the people. So is this recursive? It is, because I'm doing the same thing on the first half and then on the second half. So this is true. It has a base case because sooner or later this n divided by 2 is going to get down to one person, and I need to stop trying to divide at that point. I certainly don't want to try to help a half a person. The next one, this is a standard algorithm, but it is not a recursive algorithm. Go a mile, turn left, go a half a mile. There's nothing recursive about this, so this is not recursive. If I have to sort envelopes by zip code, I have a base case. If I've only got one envelope, I'm done. Otherwise, find the middle, put all the zip codes less than the middle on the left, all the ones bigger on the right, and then repeat. Do the same thing again with the left and with the right. Is this recursive? Yes, it is. I thought that at this point we need to look at some recursive methods. 16.2 does look at some recursive methods. It starts out with a fairly easy one, but then fairly quickly it gets down to harder one. So rather than asking you to do this right now, I thought we'll look at this easier one on Sketchpad. In main here, we call our method countdown with an argument of 2. And you remember we're trying to get our vocabulary straight now. When we write our method and we put the type before our parameter, this is a parameter. When we call our method, this is an argument. Okay, so we're going to call this method with value 2. So countInt has value 2. And if countInt is less than or equal to 0, well, it isn't. So I'm on the else. I print countInt, which was a 2. So I've got some output over here. Is it a print line? It is a print line. Let me put it here. So I'm going to print 2, and then I'm going to call my method again, but its parameter now is countInt, which was 2 minus 1. So now I'm calling countdown with a parameter here of 1. My argument here is 1. And this is why it's recursive, because countdown is calling itself, and that's what makes it a recursive method. So now I need to know, what does countdown 1 do? So when this countInt is 1, it says, is 1 less than or equal to 0? Nope. So I'm going to print my 1. And then I'm going to call countdown on 1 minus 1, which is 0. So what do I do when my int here is a 0? I print go. Print line go. And you'll notice that in this case, when countInt was 0, I do not call my method again. This is my base case. This is my stopping criteria. I have to stop. If I don't stop, I'm going to be in some sort of infinite situation, which I definitely do not want to be in. So I need to be able to stop. And the place where you stop, we always put first before we put the recursive call. So there's your order, your base case or your stopping criteria, whichever you want to call it, followed by the else situation, your call, your recursive call. We're now going to write a method to multiply a parameter by a fixed integer, by a fixed number. We're going to do it 3 times, 3 different ways. And we're going to call our methods mult by 7, mult by 8, and then mult by 9. And the reason is we're going to put them all into one Java program. And I don't want to have to comment some out. I want to be able to call each of these methods, and therefore they have to be different names. So in this first method, we're going to take a parameter and we're going to multiply that parameter by 7. And here we go, return 7 times n. Didn't even need a method to do that, but we wrote one. Now we're going to use a loop. We're going to do it with a loop, and we're going to have a parameter which we're going to multiply by 8. We start out here with total being 0. I need an n. I'm going to assume n is 4. And now I have a loop, and this loop consists of just those 2 lines because I do not have any curly braces. So I'm going to start out my I at 0. 0 is less than n, which is less than 4, and so I will go into this loop, and total is whatever it was, which is 0, plus 8. So the first time through, total is 8. Go up to the top of my loop, increment I becomes 1. Is 1 less than 4? Yes. Go into the body of the loop, and total is whatever it was, which was 8, plus another 8. So this total is now 16. Go up to the top, I becomes 2. Is 2 less than 4? Yes. Total is whatever it was before, 16 plus 8. Total is now 24. Go up to the top of my loop, I becomes 3. Is 3 less than 4? Yes. So total is whatever it was, which was 24, plus 8. It's now 32. Go up to the top, I becomes 4. Is 4 less than 4? Nope. I'm done with my loop, and I can return total. And total is 32. And we do know that 4 times 8 is 32, so we got the right answer. And here, let's look what happened in our loop. We went through the loop n times, and each time we added 8. So that's how we got 8 times 4. And now we have to think about recursion. We're going to multiply by 9 recursively. So when we program recursively, we ask ourselves 2 things. One is, do we know what the base case is? Do we have a stopping criteria? And the answer to that question is yes, because I'm multiplying n by 9. If this n is a 1, then I'm going to return 9. If I actually allowed n to be 0, I would say here, if n is 0, return 0. But I'm going to say that n has to be a positive number, and the smallest n I can have is 1. So then if n is 1, I'm going to return a 9, because 1 times 9 is 9. Done. I don't actually need an else, because if this top line, if this n equal 1 is true, I will return. If it is false, I will automatically go to the next line. And this is my recursive call. This mults by 9 method is calling itself. So if I want to multiply something by 9, let's imagine I want to multiply 6 by 9. Let's give myself a pen here. So 6 by 9, 6 times 9. Well, if somebody would tell me what 5 times 9 is, so if somebody says, oh, I know what 5 times 9 is. 5 times 9 is 45. So fine, you say, okay, then 6 times 9 is 45 plus 9, because this is 5 times 9. You know, if I ask, what is 20 times 9? And somebody will tell me what 19 times 9 is, I just have to add 9 to that to get 20 times 9. And the reason is because n times 9 is n minus 1 times 9 plus 9. That should have been a first 0, should have been a 9. Okay, so n times 9 is n minus 1 times 9 plus 9. So knowing this, I'm going to return here the 9, that's the 9 at the end here, plus multiply by 9, and my argument here is n minus 1. Let's look at how we unpack this. And by unpack, I mean, how do I know that this works? So we said here 6 times 9, so let's play with 6 times 9. So if this n is 6, n is not 1, so I'm going to return m. This is my method, this is my multiply my 9 method of 6 minus 1, 5. But what is multiplied by 9 with an argument of 5? Well, if n is 5, it's not 1, so I need to return 9 plus multiply by 9 as my method call of n minus 1. n was 5, n minus 1 is 4. So what is this then? If n is 4, it's not 1, so I'm going to return 9 plus multiplied by 9 of 3. And what is this? Well, when n is 3, it's not 1, so I'm going to return 9 plus multiply by 9 of 2. And what is this? N is 2, it's not 1, so I'm going to return 9 plus multiply by 9 of 2 minus 1, that's 1. So now n is 1. If n is 1, I return 9. So the value of this is 9. So this makes the value of this then 9 plus 9, 18. So that was M2 was 18 plus 9. So that makes this then 9 plus 18, which is 27. So that is now the value of M3. So that makes this then 9 plus 27, which is 36. And that is now the value of M4. So this becomes 9 plus 36, which is 45. And that is the value of M5. So this whole thing becomes 9 plus 45, which is 54. And that is the value of this method call, multiply 9, when n is 6. So this was multiplied by 9 of 6. Now, if you were to want to program this, you do not do this. This is showing you how it works. We have to keep on going until we find a stopping criteria, and then we can come all the way back up, calculating everything out. But that's not how you program recursively. If you try to do this, it'll drive you nuts. You ask yourself two things. One, where do I stop? Two, if I know the answer for a smaller, if I'm dealing with integers, if I know the answer for a smaller n, usually one less, how does that help me? And it helps you right here. If your programming works, so this is an act of faith. My programming works, therefore multiply by 9, n minus 1 gives me the right answer. All I have to do is add 9 to it, and I'm done. Let's look at these programs or these methods in JGrasp. So in main here, we call these methods multiply by 7, multiply by 8, multiply by 9, each with an argument of 4. So I'm going to multiply 4 by 7, 4 by 8, 4 by 9. And here are my methods written. And we run it. And we get 28, 32, and 36. 28 was 4 times 7, 32 was 4 by 8, 4 times 8, and 36 was 4 times 9. Well, the recursive problems with integers are perhaps the easiest. Let's do another example. Here we have a series, and each number doubles. Each number is twice the preceding one. I start out at 1. I'm going to say that this is n is 1 at this point. I'm going to call this the place for n equals 1, 2, 3, 4, 5, 6, 7, 8. This one would be n equals 9. So the idea here is to write a method that takes an integer as parameter, and that integer is some n, determining the place in this series, so that if, for instance, n was 9, your answer, it would return 256. If n was 10, it would return 512. If n was 1, 2, 3, 4, 5, it would return 16. So I want to write this recursively. So public static is going to return an int. We're going to call it series. It's going to take an int as parameter. Okay, did that almost without thinking. Now comes the more difficult part. Do we have a stopping criteria? Well, I can say when n is 1, I'm going to return 1. So if n is 1, return 1. Okay, but suppose n is not 1. Here n is 9. If I know the answer for 8, does that help me? Well, yeah, if I know the answer for 8, all I have to do is double it. In fact, 1, 2, 3, 4, 5, 6, the answer for 6 would be 32. But if I knew the answer for 5, I just double it to get the right answer. So otherwise, I'm going to return 2 times the value of the one before. Much easier, I think you'll agree, than writing a loop. But it requires you to think a little bit differently. And that's the hard thing for us. We're used to writing sequentially. We're also used to writing loops, but thinking recursively is new. So again, you need a stopping criteria. And then if you know the answer for a smaller number, and usually it's one less than this n, so if n is 9, but I know the answer for n equal 8, how does that help me? Well, it does help me a lot. All I have to do is double it to get the answer I need. So let's go to JGrasp. And I already wrote it in here. And those were our multiply bys from before. I put a blank line in, and now I called it with parameter 8. And it said if n equals 8, it's 128. Is that correct? Let's go to here. 1, 2, 3, 4, 5, 6, 7, 8. 8 was 128. Let's quickly see if 10 is 512. There we go. 10 was 512. Good. One more counting problem. And the idea here is that we have a line of rabbits and people. And we all know that we could never get rabbits and people in a straight line, but you know, this is a math question, so let's play the game. We have a rabbit, a person, a rabbit, a person, a rabbit, and person to infinity. We're going to number them 1, 2, 3, 4, 5, 6, 7, etc. And the idea here is that for any n, we want to know how many legs there are altogether up to and including that object with that value of n. We're going to assume there are no amputees. All rabbits have 4 legs, all people have 2. I put a list here. When n is 1, we have 4 legs because that's a rabbit. When n is 2, we've got the 4 for the rabbit and the 2 for the person, so the total number of legs is 6. When n is 3, I've got a rabbit, a person, a rabbit, and that's 10 legs altogether. When n is 4, a rabbit, a person, a rabbit, and person, and that is 12 legs altogether. N is 5, rabbit, person, rabbit, person, rabbit, and that is 16 legs altogether, and so on. Now I have to write a program that does this. I could certainly do a loop, and you can maybe see that loop, but we're going to do it recursively. So public static int numlegs, and numlegs takes some n. And the first thing I need is a stopping criteria. So when will I stop? Well, the easiest thing to say is when n is 1. So if n is 1, return the number of legs a rabbit has, which is 4. Okay, now suppose I know the answer for 1 less n. So in this case, n is 6. If I know the number of legs for the first 5, how does that help me? So if I know the number for the first 5, obviously I have to add something. But that something is different if it's a person or a rabbit. So I need to think about this. I need to add something to, so I have a recursive call. So I have numlegs n minus 1, but I need to add something to it. if n is 6, then I'll look on here. Then I'm adding 2 to my previous sum. If n is 4, I'm adding 2 to my previous sum. If n is 2, I'm adding 2 to my previous sum. In fact, if n is an even number, I am adding 2 to my previous sum. And if n is an odd number, I am adding 4 to my previous sum. So I do need an if in here. So if n mod 2 is 0, and that, so that now I'm saying if n is an even number, then I'm going to return n was an even number, I'm going to return the number of legs plus 2. I'm just going to make that on another line. For no reason, just readability. Else, I'm going to return num legs n minus 1 plus 4. Is that what we said? We said if it was an even number, so here maybe the 4, I'm going to return my previous sum plus 2. If it was an odd number, I'm going to return, so here's my odd number, the 5, I'm going to return the previous one plus 4. And just looking at this list here, that looks like it's correct. So if it was an odd number, I am going to, where is my odd number here? If it's an odd number, then I'm kind of stuck on a rabbit. So I'm going to take the number of legs previously plus the 4 legs for the rabbit. Now let's put this into JGrasp and see if it works. I have added it to our previous program. I put a heading here, people and rabbits, and then the next thing that we print out is the number of legs when n is 6. And there we go, 18. Go back over here and check, it was 18. Let's try 7. And 7 is 22. Good. Next, let's try strings. Time to move on to strings. And perhaps the first one and the easiest one is to reverse a string. So here we have a string, monkey, and we want to reverse it so that it becomes this, yaknom. And the base case is pretty easy, because if you have a null string, you just have to return a null string. But let's think about not the base case, the other case. If we have a string, we can either say, okay, if I take this substring and reverse it so that this becomes EKNOM, then all I have to then do is take this last character here and concatenate it. So then it would be y plus this. Obviously this is a string and this is a character. There's another way. I might say, okay, monkey, and if I take this substring and reverse it so that that then becomes YEKNO, then all I have to do is to concatenate on the end the first character. And it seems that these are equivalent. And in fact, they will give you the same result. So whether you take the substring from the beginning to almost the end, and then that's your recursive call on that substring, and concatenate your last character at the beginning, or you take as your substring this part beginning at the first character but going to the end, and perform your reverse on that, and then concatenate your first character. Whichever way, you get the right result. But one of these is easier and simpler to code than the other. And that's because of the substring method. So let's imagine that we have some string and we want to take this first substring here. So string, let's just call it A, is S dot. Now we want to start at the beginning, so substring from 0. Let me move this over a little bit. And then I got to calculate, so it goes up to but not including the last character. So what is the length of this? The length of monkey is 1, 2, 3, 4, 5, 6, and that means that the index of the last one is 0, 1, 2, 3, 4, 5. The index of the last one is length minus 1. So it's up to but not including s dot length minus 1. If I tried it to get this substring here, this is s dot substring 1, because I am beginning at the first character, the index 1 here, and going to the end. So this is an easier thing to write and to calculate and to think about than A. Both of these ways are equivalent, and your recursive process, your recursive thought process is the same, and your coding will be similar, but it is easier to find the substring that starts at 1 and goes to the end than it is to find the substring that starts at 0, index 0, and goes up to but not including the last index, and that last index is the length minus 1. And I think maybe here there's a comma when it should be a dot. So this way then would be the easier to code. You don't have to do it this way. I'm just saying that this one would be the easier. And here is the method. So our base case, if we've got the empty string, if S is empty, return the empty string. And that is quite normal. Normally we do this with strings. So when our string is empty, return the empty string. Otherwise, return, this is reverse called on our substring. So in this case, ONKEY, which will produce this, plus, so I'm concatenating the first character, so I'm concatenating the M. Let's go to JGrasp and see how that works. So I put it here in JGrasp. I added something to main here, reverse a string, so that we know that the next part is reversing the string. I made my string CMPSC 203. I called it, and you can see the output here. CMPSC 203 in reverse. Purposely I put a space in there so that you could see that it still worked with things with spaces in. We can try something else. Let's do a different one, not the same as. There we go. Okay, and there is computer science in reverse. Good. Since this was your first experience with concatenation and strings, I wanted to go through this a little more carefully. When we created it, we said, okay, we need a stopping criteria. And then if my method works on a substring that is just one character less than my original string, what do I have to add to it to get my results? And this is what I did. And I didn't really have to think through all the fine details and sort of unpack this to verify that it works. And I said earlier, you know, it drives you nuts if you try to think that through. But I do want to do it here to show you how it worked. So I'm going to start with a smaller string. Let's start with here. Let's start with frog. So let's go look at our code. Frog is not the empty string, so I'm going to call reverse on the substring that starts at 1, in other words ROG. So I'm going to call my method, I'm going to call my method on ROG, and I'm going to concatenate that with the character at 0, which would be F. And that would be fine, except I have no idea what reverse on ROG does. So now I need to figure that out. What is that? Once I know what that is, I concatenate it with the F. So what is reverse on ROG? Go to the method. ROG is not empty, and so I call the method again on the substring that starts at 1. So I'm going to call reverse on OG, and then add, so concatenate with the character at the first character, which in this case is R. So what is this method here, the result of this method here? Reverse on OG, it's not empty, so I call reverse on substring that starts at 1, which is G, and concatenate that with O. And then I need to move my sketchboard up a bit. Okay, now what is the effect of reverse on this string G? It's not empty, so I call reverse on the substring, and the substring that starts at 1 is actually the empty string, and concatenate it with the character at the index 0, which is the G. And reverse on the empty string returns an empty string. So the result of this is the empty string. And there's no more recursive calls. That is the end. So going backwards now, what do I have? I'll write it over here. I have an empty string concatenated with G. And that would be the result of this last part here. And that is the answer to this, what is reverse on G. So then I have to concatenate the O. Concatenate, not equals, sorry. Okay, so I've finished all of this now. I'm done with all of this. That is the answer to the reverse of OG, which I then concatenate with R. And if I could actually write a plus instead of an equals. Okay, so I concatenate with R, and all of this then is done, and that's the result of this call here. So the last thing I had to do was concatenate the F. And if I look at this string, empty string plus GORF, that is frog in reverse. So let's do another string example. Here we have a string value everyone, and we want to write a method that deletes every E in this string. So we can certainly start it off. Public static. I'm going to return a string, which is the same string just without any E's. And we'll call it deletee. And it will have a string as parameter. Okay, I need a stopping criteria, and my traditional one is the null string. So if s is, and I can do equal equal when I'm talking about null. I don't have to use the dot equals. That's one of those kind of weird anomalies. But dot equals is fine too. Why don't I do that just to show you that both ways work. If s dot equals okay. So if we've got the empty string, just return the empty string. Else. I don't really have to have the else. I don't have to write the word else, because if I return here, I will not hit the next line down. I will have returned from my method. If I didn't return here, I would automatically be on the next line down. So no else needed. It's not wrong. It just means that you have extra braces to put in and worry about. So if you can get away without writing the else, then I usually do that. Okay, so I've dealt with the base case. What about if it's not the base case? So how does that work? We said last time that the easier substring to think about is this one, the one that just excludes the first character. So if I look at this, if I can perform this, or if I can call this method on this substring and get rid of all the e's, what do I have to do then? Well, I have to attach the first character if it was not an e. Otherwise, I just forget about that first character. I just attach the first character if it was not an e. If it was an e, I do not attach it because I'm trying to get rid of all the e's. So if you like, we can split this up. Not necessary, but it might make it easier to read. String, some substring equals s dot, and we said our substring would be the one that started at 1, which is in this case VERYONE. And now I need an if s dot car at 0, and it's a character, so I can use the equal. So if it is an e, character e, then I'm going to return delete e acting on my substring. Else, so else meaning it wasn't an e, so I need to return car at 0. Got to concatenate it with so I'm concatenating that first character with everything else with the e deleted. So in this case, my first character was an e, so I would hit this first line. It is an e. Therefore, I'm going to return delete e acting on my substring. So in this case, I would return what would delete E acting on this be? V-R-Y-O-N. V-R-Y-O-N. I got rid of all the E's, and my first one was an E, so I'm just going to return delete E acting on the rest. Let's find one that didn't have an E in there. Dear. So my substring here is EAR, and my character at index 0 is not an E, so I'm at the else, and I'm going to return my first character, which is my D, concatenated with the results of performing my method on EAR, which would give me back AR. And I would get DAR, losing that E. When you're comfortable with recursion, you can write it like this and not say, well, wait a minute, how did that actually work? So I always say this is an act of faith, and I don't mean I'm appealing to a higher God here. I'm just saying faith in your own coding. You need a base case. Always need a base case, and it has to come first. If you don't hit that base case, what happens with, in the case of strings, a substring? So have your method work on a substring and then figure out what you need to do after that. So if my first one here was an E, then I'm going to just return the effects of my method acting on my substring. If it was not an E, I need to concatenate that with the effects or the results of my method acting on my substring. I think you might be ready for something more difficult.